Quiggan at Loughborough University. So I don't know about you, but I've been so impressed by those talks. They were really interesting and really clear. So I hope I can maintain a good standard for the team. So I'm going to have to speak quite quickly through this because it's a bit to get through. Most people focus much more on results. I'm going to try and take you on a bit of a story through the model that I've created with some results at the end. So the energy future of the UK is very, very uncertain. But what I'm trying to look at is the required level of demand-side management through smart metering that households could be required to participate in order to balance the grid. So energy scenarios tend to plan annualised demand and installed capacity of generators. And so that sort of time step, an annualised number, is obviously not enough. It's obviously not fine-grained enough to look at demand-side management at the household level. So what I've done is created a model, an hourly model, to look at that, and in order to sort of get around the fact that energy scenarios are quite a crystal ball gazing exercise. I've taken 6 different scenarios, and I'm going to show you 3 from deck today. So a big sort of commonality between all of these energy scenarios is that we've got a lot of decarbonisation of the supply. So we've got lots of intermittent and variable renewables, and we've got a lot of electrification of electric vehicles and heating. So we've got an increased demand and an increased variable demand as well. So these 2 factors, they really compound each other. And so this supply-demand balancing needs to happen instantaneously on the grid, and that's what smart metering within households is designed to do. So before I sort of go into the model and what I've done, I just want to really emphasise what the social science research has shown households are maybe willing to do at the moment. And we can see that consumers who are made aware of consumption during peak times will shift their demand. The Energy Demand Report project has shown that loads can be shifted by up to 10% via time series Paris. And we can expect maybe a 5 to 15% reduction in demand during those peak times. So we hold that in our head. So now I'm just going to look a little bit at 3 scenarios, these 3 deck scenarios. So we've got a nuclear scenario, a CCS scenario, and a renewables scenario. And I just want you to hold the 3rd row down, heat pumps. So in all 3 scenarios, we've got a significant percentage of heating delivered by heat pumps. 90% of heating delivered by heat pumps. That's an incredibly big heating load. And in order to manage this increased electrical load through the electrification of heating, we can see that the domestic space heating demand reduction for each of these scenarios varies between about 34% to 64%. So we're asking a lot of domestic consumers to reduce their demand, their space heating demand, whilst electrifying it at the same time. And just to emphasise, these scenarios have very different supply characteristics. So in the nuclear scenario, we've got a lot of nuclear, and renewables, we've got a lot of onshore and offshore wind. So the modelling methodology that I've applied is sort of 2-tone, top-down and bottom-up. So the top-down stuff takes lots of weather data, lots of temperature data, and demand data from Alexon, and evolves all this data under the scenarios assumptions to create a supply-demand through 11 years worth of hourly data. So we've got a large body of data. And the output of that top-down model is the demand-side management dynamics that households will have to participate in at a national level. And then this bottom-up model is populated with 1,000 households from the Irish smart meter electricity and gas trials in order to generate a sort of aggregate pool of households where the demand profile is smooth, and such that we can disaggregate these national dynamics to this aggregate household pool. And then if this text over here hadn't gone wobbly, this then says an algorithm assigns a responsibility to the household. So it looks at each individual household and says, what are you going to do within this aggregate pool in order to meet our sort of collective responsibility? I'll just skip through these because I'm going to run out of time otherwise. So this graph is going to show you the national domestic demand side dynamics. So I'm going to linger on this a little bit. What we're interested in is where is there spare capacity either side of the deficit period. So everything's been dispatched at this pump. Pump storage is gone, all the coal generators have gone, wind, everything else. But either side of the deficit period, there's going to be some spare capacity. So we need to ask, in a 2-hour window before and after the deficit period, how much is available and can that meet the deficit that we have nationally? And so we can see in these instances here, through demand-side management in domestic households nationally, we've reduced the deficit to 0. But over here there's an interesting case where there's not enough spare capacity, which is the grey one, in a 2-hour window beforehand and afterwards to actually reduce the deficit totally. So we can see the deficit post-demand-side management in the solid black line is still there. So we have these instances within the scenarios where even with a large amount of domestic demand-side management, we can't actually balance the grid. So that's an important point to take away. So now I'm going to quickly look at this bottom-up model. And so we need to say that the demand of all these households is smooth. So we need to use what's called the coincidence factor. The coincidence factor is the reciprocal or the diversity factor. And so we can think about this in terms of if all of our households coincidentally had the maximum demand through that day all at the same time, and we summed that number, that would be a really large number. But because households are different, they don't tend to consume energy at the same time, or the peak demand at the same time. So if we take the peak demand in reality and divide it by the maximum if they all coincidentally consume electricity at the same time, that's a coincidence factor. So as we have more households, the coincidence factor drops off. When it reaches its asymptotic level, we can say the demand of the aggregate pool is smooth. So we can see by the time we get to 1,000 households, which is what my aggregate pool is made up of, we can see that the demand profile is smooth. So now I'm going to, I hope you can see this. So there is a difference between what's going on nationally and what's going on in the aggregate pool. So if we look at the top graph a second, the solid black line is the aggregate pool and their demand and what's going on for them. And the dotted line, which you might not just be able to see, is what's going on nationally. And there's a difference. And that's mainly because I've had to use this Irish data set. And Irish people seem to consume electricity in a different way to English people, so fine. So what we need to do is make sure that we assign a responsibility factor each hour of the day that takes this into consideration. And so we can see that in this particular hour here between midnight and midnight, the responsibility factor is changing for our aggregate pool of households throughout the day. So we get a different responsibility factor for each 96,408 hours of the model. Okay, lots of information. I'm now going to take you to the results. So we've got 3 different types of household within the aggregate pool that I've looked at. These are based on ONS household characteristic types. Prospering suburbs, typical traits, and constrained by circumstance. And what we can see from this is that the percentage of demand reduction within these graphs is actually quite high. So I'm just going to give you a couple of numbers, if I can get them, so I can't remember them off the top of my head. So for instance, the prospering suburbs household in the morning has to reduce its demand by more than 10%, 9% of the time. And I could give you other figures like this. The conclusion is, based on our current consumption patterns, households will have significant behavioural changes necessary via demand-side management to help balance the grid under deck energy scenarios. A greater than 10% of demand reduction through demand-side management occurs regularly. Based on social science studies that I showed you at the beginning, do we think households are going to respond positively to this challenge? Thank you very much. One last thing, I've created a model. When you get to the end of these things and you create a model, you're like, okay, well, this is all well and good. If anyone has any good ideas as to how to use a model and to disseminate this work, I'd really like to hear.